So today I'm going to use OneNote rather than PowerPoint because I want to write on things as we go along. So I'm going to sit down quite a bit today. So precipitation reactions, we discussed these yesterday briefly. So what we're looking at today is presence of specific ions in solutions can be identified by observing the colour of the solution, flame tests, and observing various chemical reactions including precipitation and acid-base reactions. So we're going to be looking at precipitation reactions, we're going to be looking at colours of solutions and the observations that we would make for various chemical reactions. And in the next few days we will do a bunch of chemical reactions that will allow you to practice these things. But precipitation reactions occur when you mix two solutions together, and so in the case that we've got here, before mixing we've got a solution of silver nitrate and we mix that with a solution of sodium bromide. The solutions before mixing are just solutions with those ions in it. When we mix it together we get a precipitate of silver bromide and we end up with a solution with sodium nitrate in it. So in this case we have a precipitation reaction that is occurring. So we know that this then tells us that silver bromide is insoluble, meaning that it's not soluble, it doesn't dissolve, and in this case sodium nitrate would be soluble because it remains in the solution. So how do we find out which substances are soluble and which substances are not soluble? Well, we did this yesterday by looking on our solubility rules tables. So what are solids? So anything that's insoluble are going to be solids, and anything that's, so all of these ones here are all the ones that are going to be precipitates. So if that one, sorry, go back. So these ones are going to form precipitates. Precipitates, yep. And these ones, ignoring the obviously taking into account the exceptions, are all soluble. And these ones are only slightly soluble, and bearing in mind that our slightly soluble definition is between 0.1 and 0.01 moles dissolving per litre. So these ones are slightly soluble. And we discussed all of those yesterday. So they're the soluble ones and those green ones are insoluble. So we can use this table to predict what is going to happen when we mix two solutions together. So an example for you to look at. We're mixing a solution of nickel nitrate is mixed with a solution of potassium carbonate. Are we going to get a precipitate? So you will need your data sheet in order to answer that question. So we can write the equation where we have nickel nitrate and potassium carbonate. We'll go to, well, we've got nickel carbonate and we'll get potassium nitrate. So we know that nickel nitrate is aqueous, potassium carbonate is aqueous. So nickel carbonate, is that aqueous? Is that soluble or insoluble? Nickel carbonate. Soluble. So on our table we know that most carbonates are soluble. So most carbonates are soluble and nickel is not one of our exceptions. Sorry, most carbonates are insoluble and nickel is not one of our exceptions. So that tells you that that will be a precipitate, won't it? So that will be a solid. And potassium nitrate, our nitrates, all nitrates are soluble. So that will tell you that that will be aqueous. Yeah.
So the table talks about solubility in water. So what, in this case, are we talking about water?
Yes.
This
So you assume that we're talking about water, unless you're told otherwise.
So where does water take place?
Sorry?
So where's water's role in this reaction?
Where's water? Okay, so aqueous is telling you that it's in water.
Oh, okay.
Yep, so that's what the AQ is referring to. Yep. So we can see that potassium nitrate is soluble and nickel carbonate is insoluble, so therefore we'll get a precipitate of nickel carbonate. Okay? So that's just applying what we know, that's just applying the rules from the solubility table. And we're going to look at these equations in a little bit more detail in a moment. So our colours, writing our observations, so again we discussed this yesterday, so we can see that the colours of our substances these are the colours of our ionic solids. So copper carbonate, when it's a solid, will be green, copper chloride will be green, and so on down the list. Two colourless ions will, in general, will produce a white solid. Okay, so if it's not on this list, we assume that it's a white solid. So we know all of those colours for our. So this will allow us to predict what colour our precipitates will be. And then we have other substances. So for example, when we have copper in a solid form, it's going to be salmon pink. Gold in a solid form is yellow. Nitrogen dioxide in gaseous form is brown, and sulfur in solid form is yellow. Our halogens, in their forms that we find them in nature, gas for fluorine, chlorine, and iodine, are all gases in their natural form, and bromine is liquid in natural form, and we can see the colours there. When we put them into solution, we can see pale yellow, orange and brown for chlorine, bromine and iodine respectively. And in organic solvents, so this is going to what you were saying, Mayan, in this case this is for organic solvents, so it's not in water. And then we've got coloured ions in aqueous solution, so these ions are all those different colours. There are cations and there are anions will form those different colours. So that allows us to predict the colour of a solution based purely on the cation or the anion that's present in that solution. And that is important because we're going to talk about ionic equations, which we write only the ions that are formed participate in the reaction. So this is the kind of the process that we're going to go through. We write our ionic equation. So we write the formula of the precipitate, including our state symbol, so we know that a precipitate will be a solid. We complete the equation, and then we ensure the equation is balanced, and then we write our observation using the data sheet, the information from our data sheet. So let's talk about ionic equations. So let's go back to the equation that we dealt with before, which is nickel nitrate. I'm just going to make some space in here, sorry. So we've got nickel nitrate. So I think nickel is 2+, isn't it? So we should actually have 2 here. That's balanced. And we'll have 2 of those. So nickel nitrate plus potassium carbonate going to nickel carbonate plus potassium nitrate. Now, because our reactants are in solution, they're dissolved in solution, they're aqueous, they're not actually in solution as nickel nitrate and potassium carbonate. They're actually in solution as nickel ions, nitrate ions, potassium ions, and carbonate ions. So when we get nickel nitrate as a solid and we add it to water, we end up with nickel this equation happening. So water is a liquid, and water is a liquid there. So what we're ending up with, we're ionizing, we're breaking down the ionic structure of nickel nitrate, and we're producing nickel ions and nitrate ions in solution. So we also know that carbonate, the solid carbonate, when we add that to water as a liquid, we'll end up with potassium ions and carbonate ions with water as a liquid. So if we were to write this equation at the top in terms of ions, we actually have nickel plus nitrate plus potassium plus carbonate, all as ions. And we end up with, now nickel carbonate is the solid that precipitates out, so we end up with nickel carbonate as a solution, as a solid, and that means we still have nitrate ions and we still have potassium ions. Okay, everyone happy with that? So all we've done is we've taken these two equations and we've combined them together to form an overall equation here. Yep.
So is there like a general formula? Is there like a specific pattern that these things follow? Like that last one?
Okay, so let me just finish. Yep. So, are there some ions that are on both sides of the equation? Which ions are on both sides of the equation? So, the nitrate and the potassium and the nitrate. The nitrate. So these ions are what we call spectator ions. They don't actually take part in the reaction. So, because they don't take part in the reaction, when we're writing an ionic equation, we don't include them in the reaction. So, when we write an ionic equation, I'll come to you in a second, we will simply write this as Ni2 plus aqueous plus carbonate goes to nickel carbonate as a solid. So that would be the ionic reaction that we would write. Because the nitrate and the potassium are spectator ions. They're on both sides of the equation, so they're not involved in the reaction. Okay? Hang on, we'll go. Oh, this one here? Yeah, I didn't put that in there because I was going to get rid of I knew that potassium and nitrate were spectator ions. So if I was writing this one here, so I've got my 2 potassium here, and I've got my 2 nitrate here, but when I'm writing my ionic equation, I could put where we had 2 nitrates and 2 potassiums, 2 nitrates, 2 potassiums. Yep. Because if they're not spectator ions, if nickel was only +1 charge, then I would need 2 nickels to balance, so I would have to have that in my balanced ionic equation. Okay? Yep.
So how do you know that the nitrate and the potassium are spectator ions?
Okay, I know that they're spectator ions because when we put the two together, when we put the 2 solutions together, the solution which has got nickel nitrate and potassium carbonate in them, when I put those 2 solutions together, a reaction occurs, and the reaction produces a precipitate, a solid, which is this one here, nickel carbonate. All right, so I get nickel carbonate being produced, and in order to produce nickel carbonate, I'm reacting nickel and carbonate, so potassium and nitrate are not involved in that reaction. So that's why they're spectator ions.
But why aren't they involved in the reaction?
Well, what we started out with was nickel, so that's potassium. So this is what we started with. Over here, that's what we start with. And that's what we end up with. And we can see by that reaction that the nickel ion combines with the carbonate ions and forms a nickel carbonate solid, a precipitate. So that's the reaction that occurs. And the nitrate ions end up as nitrate ions at the other end of the reaction. And the potassium ions end up as potassium ions at the other end of the reaction. So they're just spectators. They're just watching the reaction go on. They're not involved in the reaction. Okay? So the potassium could equally well have been sodium and it would make no difference to the reaction. Okay? So that's the concept of ionic equations, and we're going to get some practice at writing some of those in a moment. So what we need to be able to do is to identify the colour of the solutions, the colour of the precipitate, and the colour of the resulting solution. So, what would be the colour of nickel nitrate? in a solution, yep. So nickel in solution, if we look at our coloured ions in aqueous solution table, come back up here. Oh no, go down, sorry. So we can see that nickel is green. So our nickel nitrate solution would be green. And what would our potassium carbonate solution, what colour would that be? So we can see that it's not, so potassium is not one of our coloured ions, carbonate's not one of our coloured ions, so that would be a clear solution. So we would have a green solution that we're mixing with a colourless solution. When we mix the two together, what happens? A precipitate is formed. And what colour is that precipitate? What colour would nickel carbonate be? So we look on our ionic solid list. Nickel carbonate is not on the list. So therefore it would be a white solid.
It says the ionic solids are the same colour as the colored ions they contain. The difference green when the solids are big.
Oh, sorry. Yes, you're right. So, in general, ionic solids have the same colour as the... ionic solids have the same colour as that of any coloured ion that they contain. So, they would have... it would be white if they weren't coloured. So it would be... we would end up with a green precipitate because we're getting nickel carbonate. If it was potassium carbonate being precipitated out, that would then be a white solid. Yeah. And what would happen to the solution? So the solution would become colourless, wouldn't it? Because the nickel, which was making the solution green, is coming out of solution into the precipitate. So the ion that's making the solution green is no longer in the solution, therefore the solution becomes colourless. All right. So there we go. The ionic equation, what we had before. We have nickel 2 plus in solution plus carbonate in solution goes to nickel carbonate, which is a solid. The observation, a green solution is added to a colourless solution producing a green precipitate, and the solution becomes paler green, so it's going colourless. Okay? So notice what we're doing when we're writing our observations. We are noting this is solution 1. So solution 1 is added to a colourless, so this is solution 2, and producing a green precipitate. So this is product 1, and the solution becomes paler green, so this is the final solution, or we could consider it to be product 2. Okay, so we have 2 things to start with and 2 things to finish with, and we have to describe both of those things. We've got 2 solutions, we describe both of the solutions, we end up with a precipitate and a solution, so we describe both of those. If we didn't end up with a precipitate, if we just ended up with a solution by mixing 2 solutions together and there was no precipitate formed, then we would describe the colour of that solution. And we'd obviously describe that no precipitate was formed. Yep. Nickel carbonate is green because, in general, ionic solids have the same colour as any coloured ions they contain. So nickel is green, so it contains the nickel carbonate contains the nickel ion, so therefore it's green in solid form. Well, carbonate's not on our list, so we assume that it's it's not going to control the colour. So if it's mixed with something else that doesn't control the colour, then it'll be white. So potassium carbonate, for example, would be white.
It's like a blend between the two colours, like green and white.
No. So potassium doesn't have a colour. Carbonate doesn't have a colour. When you get two things that don't have colours combining together to form a precipitate, you get a white precipitate. Okay, so let's do some practice. Where I want to go over here. No, I don't. Okay, so first of all, I want you to identify... No. Come on. Determine whether they are soluble or insoluble. So it's a direct application of using your data table. So on your data sheet, you're just going to use those solubility rules, use the solubility table to determine which ones of these are soluble and which ones would form a precipitate. So feel free to discuss on your table or work with your partner or work individually. Once you've done a couple, check with your table to make sure that you're on the right track.